I'm going to jump around a little bit just because I like to put all my hydration reactions together. So, people were looking at this hydration, or the hydration of the alkenes, follows Markovnikov's rule, and then someone says, well, I don't want to follow Markovnikov's rule. Can I have the hydrogen go on the carbon with fewer hydrogens? Basically saying, I don't want to put my OH on the more substituted carbon, I want to put my OH on the less substituted carbon. So guess what? If we need to do something, we find a way with some fairly specific reagents. H2SO4, very general reagent. But let's look at the next thing, hydroboration oxidation. It'll also convert an alkene to an alcohol in 2 steps. But here's the deal. There's no carbocation. When you take a double bond and add BH3 to it, the boron goes on one carbon, the hydrogen goes on the other carbon, but it turns out the boron bonds to the less substituted carbon. The boron goes on the carbon with more hydrogens, which means the hydrogen went on the carbon with fewer hydrogens already on it. And note, the boron and the hydrogen always must add from the same side, syn addition only. So not only do you get the hydrogen on the carbon with fewer hydrogens, we call this anti-Markovnikov. You get anti-Markovnikov addition of that hydrogen, syn addition only, but now we've got a BH3 and an H on here. We can convert this BH2 and an H on here. We can convert this BH2 to an OH with hydrogen peroxide in basic conditions. So this is a 2-step reaction right here. So note, if we have this cyclohexene with the methyl group on it, recall when we added just H2SO4, if we'd add H2SO4 and water, Markovnikov's rule said the OH would go on the more substituted carbon. With BH3 and H2O2, we know we're going to put the OH on this carbon down here. The hydrogen will go on the carbon with fewer hydrogens, anti-Markovnikov. Therefore, the OH will go on this carbon down here. Also note that this generates a chiral carbon, 2 chiral carbons. So if the hydrogen comes in on the backside, oh, but here's the deal. If hydrogen came from the backside, which side does the OH come in on? Note, syn addition only with hydroboration oxidation. So if the hydrogen came from the backside, the OH has to come in from the backside. If hydrogen comes in from the top side, then the OH has to come in from the top side. So we get the 2 enantiomers, but we don't worry about diastereomers because we can only get syn addition only with hydroboration oxidation. All right. There's another reaction. It's not in your book, and that's a pity. I think the reason it's not in your book is because, you know, it's very, very, very nasty, as we're going to find out. But it is oxymercuration demercuration. It is another way to add water across the double bond. We're going to take an alkene and convert it into an alcohol. And the process is one, oxymercuration. You take this mercury with OAC, that's acetate, OC double bond OCH3. A mercury 2+ with 2 acetates on it. In THF, tetrahydrofuran with water, that's the first step. That's our oxymercuration. Then we do demercuration with sodium borohydride. NaBH4 is sodium borohydride and OH-. Note, oxymercuration, demercuration puts OH, water, across the H2O across the double bond, and our OH goes on the more substituted carbon. The hydrogen goes on the less substituted carbon. And now at this point you're saying, wait a minute, that's what H2SO4 will do. This is Markovnikov's rule. The OH went on the more substituted carbon. H went on the less substituted carbon. That's Markovnikov's rule. Yeah, this is Markovnikov's rule. Now, I've looked up and I can only find examples of anti-addition, but I have not been able to find any place that says it can only go anti-addition. So truthfully, I'm not 100% sure about the stereochemistry here. I've not been able to find anything that says anti-addition only, although all of the examples I've seen have been anti-addition. So why do this oxymercuration, demercuration? Well, the big reason is, while it does Markovnikov's rule, like sulfuric acid, it does not go through the carbocation. There's no carbocation in this reaction, so there are no rearrangements, and this is the main reason to use this. If you want to add water across a double bond, following Markovnikov's rule, yeah, H2SO4 will do it, but that could lead to rearrangements. This will have no rearrangements in that case, and that's why it's done. Another nice thing about it, it's very fast. This oxymercuration takes 20 seconds. Yeah, you set up your glassware. It took you a half hour just to set up the glassware and get everything ready. Do the oxymercuration 20 seconds, and then you don't even have to get the product. You just, when you're done with that, boom, you throw in the sodium borohydride and base, and in 6 minutes later, you've got your product. This is awesome. It's very fast. It gives you very high yields, greater than 90%. This reaction just works wonderfully. The problem with it, it is very, very toxic. This mercury compound right here, this mercury acetate compound, and some of the other products of the reaction that we're not going to go into are just extremely toxic things. They are the kind of thing that if you get one drop of this on your gloved hand, this mercury compound will go through the glove, go through your skin, and you'll be dead in 2 months. Now, if you happen to see that drop of mercury go on your glove, you can quickly take off your glove, quickly wash your hands, and then go to the hospital and say, hey, I've been mercury poisoned, and then they can treat you for the mercury poisoning. The problem is, most of the time, because you've got a glove on your hand, you don't feel it when you get this drop of the mercury compound on you, and if you don't feel it, then a month later you're just really tired all the time, and then they found out after a month of tests that you've got mercury poisoning, and then by that time it's too late. They can't save you, and you know at that point you only have a few weeks to live, and there's nothing that can be done for you, and you're dead. Happened to a very up-and-coming chemist that just didn't know how, but got a drop of one of these mercury compounds on the glove and died 2 months later. And by the time they figured out what the problem was, they said, here's the deal, and we can try to treat you, but there's a good chance you'll die from the treatment, or we got like probably, I don't know, probably less than 5% chance of living through this either way. And so this person took the treatment and died. But they knew what the deal was, so they got all their affairs in order, and then just said, okay, all my affairs are in order, let's do this thing, and died a week and a half later. Ooh, well, that's fun. Let's look at something better. Let's assume we take all proper conditions, and let's look at this. Okay, here is the same compound. We're going to start the same compound here, this alkene. What would we get if we did oxymercuration, demercuration? What would we get with just standardized acid catalyzed hydration? What about hydroboration oxidation? Well, oxymercuration, demercuration, we know is going to add OH, H2O, water across the double bond, and the carbon with more hydrogens, Markovnikov's rule, will get that hydrogen, which means the OH is going to go here. And since there's no rearrangements possible, we know that's it. Hydrogen goes here, OH goes here, that's our product. Sulfuric acid, acid catalyzed hydration. Okay, Markovnikov's rule, we know the hydrogen's going to go on this carbon here, which means the OH would go here, but it starts as a carbocation. We note, oh, that will make this a secondary carbocation. A hydrogen will move over and give us a tertiary carbocation over here. We realize through rearrangement that the OH is going to end up on this carbon. The OH ends up here. Hydroboration oxidation, anti-Markovnikov. Hydrogen and no carbocations, no rearrangements. Anti-Markovnikov, hydrogen goes here, the OH goes on the end. So this is a nice set of 3 reactions where we can decide where the OH goes. Where does the hydrogen, where does that alcohol end up? We can decide as chemists where it belongs.